So in this video, I'd like to go over the principle of virtual displacements at the structural level. So with the PVD, we're going to treat displacements as if they are virtual, and the forces are going to be real. All right, so this is kind of the counter or the opposite to the PVF, where we treated the forces as virtual and the displacements as real. Okay, so considering that we use PVF for compatibility equations, the counter to that is that the PVD will be used to generate equilibrium equations. And that, in the end, will allow us to bypass statics, which I think will make everybody happy. Okay? So, kind of the PVD for a structural system going very broadly here, right, is assume we have a system where we have nodal loads P sub F at the unconstrained degrees of freedom, reactions P sub C at the constrained degrees of freedom, and then member loads, I'll just call that W, all in equilibrium with the internal forces of each element. All right. So when we have equilibrium, whenever we apply an arbitrary virtual displacement field indicated by delta UF and delta UC at the unconstrained and constrained degrees of freedom respectively, the external work done at the unconstrained and constrained degrees of freedom, as represented by these dot products or inner products in equation 1, is the external work. All right, and then the internal work is going to be the sum of all the element contributions of the real forces, including the effect of member loads, okay, acting through virtual displacement fields, delta U sub L, that are compatible with delta UF and delta U sub C. Okay, so recall that the local forces for an element, say for a frame or truss element, is given by this relationship. Okay, so it's transforming the basic forces to the local degrees of freedom and then adding in the so-called reactions of the basic system due to member loads, PLW. Okay, so we need to look at internal work at this level or the global level, either one, but it's a little easier to do local, so that we're sure we get the rigid body effects of member loads. Okay, but at any rate, that's the internal work. And then the statement of the PVD is that the external work is equal to the internal work. Again, where we have compatible relationships between delta U sub L and then delta UF and delta UC. Okay. All right, so that's the local basic transformation is shown down here in equation 4. Okay, but this footnote just kind of reminds us that in the PVF we just kind of disregarded member loads because forces were arbitrary, right? So we just set them to 0 at our convenience. But now forces are real and we have to include those effects. All right, so the internal work calculation is a little more complicated. Okay, but we can carry through our equilibrium relationship. All right, dig a little deeper into equation 4. So if we were to multiply both sides of this equation by our arbitrary local displacements, all right, we'd end up with this left-hand side and then these terms on the right-hand side. Okay, then using the real compatibility relationship shown here as our virtual, all right, we get delta UB equals ABL delta UL. Okay, so read it from right to left. Virtual local displacements given, transform to the basic system with ABL, they end up with compatible virtual basic deformations. All right, so putting that into this expression here, all right, recall the transpose of a product is the inverse sequence of the transposes. I'll write that out. That probably made no sense. but AB transpose is B transpose, A transpose, okay? So that's where delta UB transpose becomes this, right, from the transpose of this equation here, okay? So again, just kind of going through some linear algebra to get down to the punchline, okay? But basically what this does is it separates the virtual work due to basic forces, which is right here, from the virtual work done by member loads, okay? So when we plug that into our right-hand side of equation 3, or our PVD statement, all right, we have a term involving basic forces and a term involving member loads, all right? And we get external work, okay, it equals the internal work, all right? But we're skipping a few steps here, all right? But basically moving all the effect of member loads, which are basically external effects, right, to the left-hand side. So that's where we get this negative sign. Right? And then we have delta capital UB, which collects all the element basic deformations, virtual, with inner product with all the real basic forces, P sub B. Okay? So delta UB transpose PB, all right, is just the collection of all the delta UB transpose PB for each elements, or for all elements, okay? The concatenation, right? Okay, so through a little more hand waving of transformation and assembly, we can show that this term right here, all right, the summation on the left-hand side, is equal to delta UF transpose PFW plus delta UC transpose PCW, i.e. the work done at the unconstrained and constrained degrees of freedom due to the equivalent loads coming from our member forces, our member loads, okay? And then we get down to our virtual work equation in a form that looks a lot like the PVF, all right, but this is the PVD, okay? But we have on the left-hand side the equivalent nodal loads at the constrained or unconstrained degrees of freedom, and then the equivalent nodal loads at the constrained degrees of freedom. And then on the right-hand side, we have the effect of all the basic forces, okay? Okay, so you can kind of read through this explanation, all right? But then the compatibility relationship relates our virtual nodal displacements, which are on the right-hand side, okay, using the compatibility matrices AF and AC to give us the compatible virtual basic deformations. And I'll show examples of this in another video, okay? All right, so what this does is it allows us to, as we'll see in the examples in other videos, allows us to generate equilibrium equations to relate external loads and reactions to our internal forces of a structural system, okay? So again, it'll allow us to bypass statics, which is pretty nice, okay? And again, that'll be shown in some examples, okay? Okay. So we can also look at the at only the constrained, or excuse me, the unconstrained degrees of freedom, the subscript F, all right, and we get the basically what we recover for non-trivial solutions of or selections of delta UF. All right, if this is non-zero, then we're left with our nodal equilibrium equations, which should look pretty familiar from previous lectures, where we recall the AF transpose is equal to BF. All right, the equilibrium matrix is the compatibility transpose. Okay, all right. So for a lot of these, when we apply the PVD, it'll be a lot like the PVF. All right, we'll kind of just set arbitrary values of delta UF. It'll be like all zeros and then a 1 and then a 0. All right, and then like delta UC might be all zeros as well. All right, so it's all zeros and ones in those delta UF and delta UC, and then from that, from the compatibility matrices AF and AC, we'll get the element deformations that are compatible with our virtual displacements. Okay. All right, and with that, I'll conclude this video and then finish the notes in another video.